welcome to this class on circuit theory. In the last class we have discussed on nodal analysis. Nodal analysis is one method by which we can write the equations for the circuits in a systematic way. Now in this class we will discuss on the second method called mesh analysis, which is again which is helpful to write the equations for the circuits. Okay, so in this class first we will discuss, before going it into the details, first we will discuss what is the condition where mesh analysis can be used, or what is the condition, in which condition mesh analysis can be used. Then we will have the steps involved in order to carry out the mesh analysis in the circuit. Then we will see the examples, circuit examples with resistive networks, and there we'll see the circuit with resistive elements where it consists of the independent sources, and also we will write the equations for the circuit or for the network with resistive element when it consists of the dependent sources. Okay, once we will be familiar with this, then what next we will see the resistive circuit or the resistive network where there will be only the current sources present. Okay, in this independent voltage sources, let me write here the dependent voltage sources. Okay, then we'll see the resistive network, or we'll write the mesh analysis for the resistive network when there will be only current sources, and there will be two ways or two situations you can find out the current source. One, you can find out the current source in the outer loop or outer mesh, and another way you can find out I'll write here the current source in outer mesh. And also, how can we write the equation if the current source will be present in the common mesh or common branch between the meshes. Okay. So these are the things we will discuss in this particular class. So let us start with the condition where the mesh analysis can be used. Before going into detail, as we have seen that in general the nodal analysis is completely the completely generalized method by which you can write the equations for any electrical circuit. Now in the second method, that is called the mesh analysis, which is also helpful to write the network equations, but this mesh analysis cannot be applicable for all the generalized circuits. There is one condition where the mesh analysis cannot be used, and the condition is that when the network is non-planar, then we cannot use the mesh analysis. Okay, so it means that what is the condition for the mesh analysis? The condition for mesh analysis that your circuit or network, let me write the circuit must be planar. Okay, so now the question comes, what is the planar? So let us have with the example first. So in order to understand the word planar and non-planar, let me first draw the skeleton of the network. Suppose this is 3 dimension like this, for example. Now this is what inside the branch, this is, let's say, and these are the terminals. Okay, So this is one skeleton, and second skeleton let me draw like this. For example, suppose this is the way. Okay, and these are my terminals. One is terminal is here and second terminal is here. So this is second skeleton. So here, if I would like to identify which one is a planar and which one is a non-planar network, so we can say here is that first network is, this is non-planar network and this is your planar network. Now let us have the definition on the identification of non-planar and planar network. So here you can say that the sum of the branches in this network has been overcrossed or undercrossed the another branches. So here you can say these three branches are are the crossing the other branches, whereas you can see that there are no branches which are crossing each other. So in short, the circuit is said to be planar if it is possible. Let me write it here. So if it is let me write here. So the network is said to be planar if it is possible to draw the diagram of the circuit or to draw the circuit on this surface or on the plane surface. Okay, and on the plane surface draw in such a way that no branch over or under any other branch. So this is the proper definition of the planar. So the network said to be planar if it is possible for me to draw the diagram of the circuit on the plane surface in such a way that there are no branch over or underpass. Okay, no branch passes. You can say no branches passes over or under any other branch. It means the circuit which can be drawn on a plane without crossing branches. So if you come to this network here, you can say that this is passing under the branch, so this will not come under planar. Here you can say that there are no branches passing each other, that's why this is my planar network. Okay. With one or two examples we will see with the skeleton to identify the planar and non-planar network. Okay. So suppose if I draw the skeleton like this, something like this on the plane surface, and this is my diagonal element, and suppose one more diagonal element is there. So suppose these are my terminals where I can connect the source, for example. So here if you identify as per the definition, we said that the branch should not be a overpass or underpass, any other branch should not cross each other, right? So if you say this is what it is, not passing the branch. Basically this I can redraw as like this also. Okay, and from here to here, instead of drawing from here, so I can draw like this, so that there will not be any branch cross each other. Okay, so it means that this skeleton is your planar network. Okay, so with this I can identify whether it is planar or non-planar. So here we can observe that there are no branches passing over each other. Suppose to it one more way, let me draw another example. Suppose this is my network. Okay, and this is branch connected here, and one more branch is like this. Okay, so these are my nodes. Now let us identify whether it is planar or non-planar. So if I would like to redraw it also, so suppose if I am redrawing it, let's say like this branch, if I am redrawing like this, okay, so what I observe, it will cross this branch. Okay, so this is not possible in order to have the planar thing. Now what is other way? Other way is I can redraw like this, but here also I am observing that this is crossing this branch, that's why this is also not possible to have the planar. So ultimately this skeleton of the network which we have drawn is a non-planar. So if this is the network, then in this particular kind of skeleton it is highly difficult to draw or to apply the mesh analysis to write the equation. So in short, mesh analysis is applicable only for the planar network, and why you will be able to come to know at the end of this class. So let us start with the steps involved in the mesh analysis. So first you make sure that the circuit is confirm the network or the circuit is planar. If it is planar, then you can go with this you can go with the second step. So circuit has to be planar. If circuit is non-planar, you cannot apply the mesh analysis here. Once you have confirmed that okay, network or circuit is planar, then you identify the mesh currents. Okay, and in order to find out the mesh current, in order to they identify the mesh currents, I should say that identify the meshes instead of saying mesh current. So next you identify the meshes and assign clockwise, depends. Okay, so here I'll use this, that assign clockwise mesh currents. I will say clockwise currents in each mesh. For example, I1, I2, etc. Then third, once I have found out the meshes, once I have found out the mesh currents, then next what you do, apply KVL in or at each mesh, and then repeat the procedure for the other meshes also. And at the last you formulate the resulting expressions which you will obtain from all the meshes into linear algebra form. And once it is into the linear algebra form, you know how to solve or how to find out the solution. So, and that general linear algebra form will be, you will get it as like, that is impedance matrix into current vector, which will be equal to voltage sources vector. Like in nodal analysis, what we got it in the linear algebra form, that is the admittance matrix into unknown voltages, which will be equal to current sources. This was for nodal analysis and this is for mesh analysis. Now before going into, let me again tell you the difference between mesh and loop. Basically, if I'll draw like this again, suppose this is my skeleton. So here if I would like to identify which is mesh and which is node, already we have discussed this. Loop is what your generalized loop. If I am starting from here and if I am reaching from anywhere to the same point, then that is your loop. But mesh is also kind of loop, but inside that loop there should not be any other loop present. Okay, so there should be only one loop. Okay. So this will be mesh 1. Here also I am finding that there is no other loop present, so this is mesh 2. And if I'll say this will be your loop. Okay. So with this understanding, let us take it the example and let us try to formulate it into linear algebra form. So let us see with the one resistive network. Suppose there is the voltage source present, there is one resistor like this, then one more register here, then one more register like this, and then suppose one more voltage source, and these are my polarities, and this is ground. Okay. So first identify whether it is planar or non-planar. Yeah, it is planar. I observe that there are no branches crossing. So let me name the battery. So suppose this is my E1 with the given polarity. This is for example R1. This is R2, and this is my R3. Okay. Now suppose this is one more thing. These are my polarities and named it as E2. Okay. Now suppose find out the meshes. So I observe that there are two meshes, and also we know that number of branches are equal to number of nodes plus number of meshes minus 1. So with this also you can find out how many number of meshes present in it. So it will be number of branches minus number of nodes plus 1. So how many number of independent meshes present here? So number of branches are that where it means number of elements. So 1 2 3 4 5. So 5 branches minus number of node. This is one node, second node, third node, and this is common 4 nodes. So this is 4 plus 1. So how many number of meshes will be? Independent meshes will be definitely 2. So this is your one mesh and this is your second mesh, because you observe that there is no other loop present inside of it. That's why I can call it as the mesh. Then next assign the mesh currents in clockwise direction. So suppose this is my I1 mesh current and this is my I2. Okay. Now with this let us have the polarities. So current is going this way. So this is plus, minus, this is plus. There is no unique rule. You can choose by your own. Okay. This is plus, minus. Okay, that way. Now suppose write the equation for mesh 1. So in order to write it, apply the KVL, and we know KVL that sum of all the voltages in each branch, if you sum it out in the loop, it will be equal to 0. So what it will be, let me go from this to this. So here the battery is present. So let me write KVL for M1, and let me M1 is my mesh 1. So if I am going from here to there is a voltage rise by E1. Then if I am going from here to here, so now what is the current flowing? So we assign that I1 current is flowing. So it will be minus I1 into R1. Again, now if you look here, I1 is also flowing, I2 is also flowing. So it is I1 minus I2. I1 minus I2. Okay. Now what I will do, this is again there is a drop, so negative sign into R2. Yeah, negative, there is a voltage drop, so that's why negative sign. Okay, minus R2 into I1 minus I2. Again this, there is no element in this branch, so it will be 0. Voltage is 0 here, as it is simply wire, and this will be equal to 0. Okay, so let me write in other way, that is E1 will be equal to I1 R1 plus I1 R2 plus R2 into I2, and if you take it I1 as common, so you can write R1 plus R2 into I1 plus R2 into I2. Okay, this is for mesh 1 and this is for mesh 2. So suppose now if I am considering mesh 2, positive negative, current is going this and this way with this much current, so it will be, I can say that I2 minus I1, because I am considering separately now for mesh 2. That's why I am using this polarity. Let me draw with other pen. So suppose this is for mesh 2, and which current will be I2 minus I1 in this particular branch. Okay, so for that mesh 2, let me start from here. So now there is a drop, so drop means what? It will be minus R3 into I2. Again if I am going from here to here, so again there is a drop, so it will be minus C2. Again I am going from here to here, so this will be positive negative, so again there will be drops, which will be minus R2, and current will not be I1 minus I2, but it will be I2 minus I1, which will be equal to 0. Now I want the resistors values as positive, so this also I can write according to my convenience. Minus E2 will be equal to R3 I2 plus R2 I2 minus I1, and if I solve this, it will be what? R2 plus R3 I2 minus R2 into I1. Okay, so this will be minus E2 will be equal to R2 plus R3 into I2 minus R2 I1. So this is equation 1, this is equation 2, equation 1. Now let me write into linear form. So what you can observe that, okay, I1, I2, these are my unknowns, E1 and E2, these are my known things. So this you can write as I1, I2, and which will be equal to the sources. So in equation 1 it is plus E1, equation 2 it is minus E2. And what is this? R1 plus R2, so this will be R1 plus R2. Okay, somewhere wrong here. So if I am shifting here, I1 R1 plus R2 I1 minus I2 will be there. So it will be I1 R2. I am sorry, so this will not be plus, this will be minus. Okay. So this will be minus. So R1 plus R2. This will be minus. So this is minus R2. Then for equation 2 it is minus R2 and this is R2 plus R3. Okay, so now if you look this matrix carefully, what you can observe that the diagonal elements which you are observing are nothing but the sum of the resistances which are connected in that particular mesh. So if you look at mesh 1, what are the resistances connected? R1 and R2. Okay. So R1 plus R2 diagonal entries will be nothing but the sum of resistances present in that particular mesh. So if you look at mesh 1, it will be R1 plus R2. If you look at mesh 2, it will be R2 and R3. So this diagonal entry will be R2 and R3. And the off diagonal entries will be the common resistance between the meshes with the negative sign. So you can observe that R2 is the common between mesh 1 and mesh 2. That's why this will be the R2 with the negative sign. And then the I1 and I2 will be your unknown mesh currents, and here it will be the voltage sources values. Again you observe that this is plus E1 and this is minus E2. So what is the significance of it? So again you can think of like this. So here what I assume, my current direction is like this. So current going away from the positive terminal of the battery E1, that's why I can take it as the positive sign. Whereas you come to here and which direction we assume like this. Now here I am observing that current is going into the positive terminal of the battery. That's why I can say that the sign of the E2 is negative. Okay. It means current coming from the battery, then take it positive, and if current going into the positive terminal of the battery, then take it negative sign. Okay. So this is also one of the way that shortcut you can use it to write the equations. And you observe that this will be the impedance matrix, this will be the unknown vector I, and which will be the sources present, and which will be voltage sources. And from that you can find out the unknown vector mesh current like this using Z inverse into E vector, and Z inverse, you know, this way you can find it out, adjoint of E and divided by determinant of not adjoint of E, it will be adjoint of Z into determinant of Z into unknown vector. And in order to have solution, your determinant of Z should not be equal to 0. And what is the significance of determinant? That already we have discussed during the nodal analysis. Okay, so this way you can solve the circuit using mesh analysis. Now let us take it let us draw one network and let us directly write the mesh equation in linear algebra form. So let me draw the circuit. It's like this. say battery source present there. Then there is the battery source resistor, and then all are connected like this. Let us name. So this is plus E1. Suppose this is R1, R2, this is R3, R4, R5, R6, and say this is E3, and this is E2, and suppose this is E4. So now first it is planar, obviously. Okay, so we can apply the mesh analysis. Now let us draw the anti-clockwise mesh current. So suppose this is I1, this is mesh 2 I2, this is mesh 3 I3, and this is one more mesh I4. Okay. Now let us directly write the equation. Observe that there are 4 meshes. Okay, so how many, the number of elements? It will be, there will be 4 mesh currents. So the size of matrix, it is square matrix basically, and it will be 4 by 4. So let me write first unknown I1, I2, I3, and I4. Then let us write the diagonal elements. This is them. Okay. Now let us write the diagonal element. So first diagonal element will be the sum of all the resistances present in loop 1. So it will be R1 and R2. So it will be R1 plus R2. In mesh 2, R2 plus R3 and R4. So second will be sum of resistances present in mesh 2. In third, R4 and R6. So it will be, sorry, not R4 but R5 plus R6. In mesh 4, R3 and R4 resistances present in the mesh. So it will be R3 plus R4. Okay, again one more point I have forgotten to tell you. From there, one more conclusion we can draw that. As we observe that it consists of independent voltage sources, that's why the off diagonal elements or the matrix will be symmetric matrix. Okay. So if there will be independent sources present, then the matrix, what we will get it as the impedance matrix, will be always symmetric. And if there will be the dependent sources present in the circuit, then we will not get the symmetric matrix. Okay. So you can observe that a minus R2 is common between mesh 1 and mesh 2. Okay. So here we can say that there are no dependent sources. Obviously the Z matrix or the impedance matrix will be symmetric matrix. Okay. So what is the common resistance between mesh 1 and 2? That is R2. So it will be negative R2. And same way with this is 1, 2, 3, 4, 1, 2, 3, 4. So between 2 to 1, mesh 2 to 1, it is R2. So it is minus R2. What is the common between 1 with 3? There is no common, so it will be 0. So 3 and 1 is 0. What is the common between 1 with 4? It is no resistance is common. So 1 and 4 is 0. 4 and 1 is also 0 because of the symmetry. And this symmetry will come because of the independent voltage source. Okay. Then next we'll see what is the common between mesh 2 and mesh 3. Yeah, R5. So it will be minus R5. 3 with 2 is minus R5. What is the common between mesh 2 to 4? So between mesh 2 to 4 is what? 2 to 4 is R3. So it will be minus R3. And 4 to 2 will be also minus R3. 3 to 4, there is no common resistance connected, so it is 0. This is also 0. Now let us come to all the voltage sources present in the network. So here you can see that current is coming out from this battery E1 and it is going into the negative terminal of this battery, or again coming out from positive terminal of the battery. Okay, so it will be sum of all the voltage sources. So it will be plus E1 plus E2 also. Okay. In mesh 2 you can see that this is our assumed direction and it is coming in the positive terminal of the battery, so this will be minus E2. For third, it is coming in, the current is going into the positive terminal of the battery, so this will be minus E3, and again you can see that again going into the positive terminal of the battery, so this will be also minus E4. Okay, so with that you can express this as the impedance matrix into unknown vector, which will be equal to voltage sources present in it, and from that you want to find out the mesh currents, and that can be obtained using Z inverse with voltage source V can. Okay, so this way you can solve the network. Now let us take it one example with the dependent sources, and let us prove that if it is a dependent source, then the impedance matrix will not be symmetric matrix. Okay, so let me draw again the network, something like this. This is my R1, this is a dependent source, and this is current controlled voltage source. And this is R2, this is also current controlled voltage source. This is R3, and this will be my battery connected like this. So suppose these are my convention, this is E1, R1, then suppose this is Rn into I2, this is suppose R2, R3, let us randomly assign the variables plus E2, and this is suppose Rm into I2. Okay, so suppose give the polarities plus minus, identify with the assign the mesh current. This is 1, this is mesh current 2, this is polar, so planar, this is plus minus, this is plus minus, plus E2. Okay, now let us write directly, use the same procedure what we have done it. So consider for mesh 1, so there is a rise, if I am going from here to here, so it is plus E1, then there is the drop, so it will be minus R1 into I1. I am going from plus to minus, so there will be drop, so it is how much source Rn I2, then again there is a drop, so this will be I1 minus I2. If I am considering first the mesh, then there is a drop obviously, so minus R2 into I1 minus I2, again there is a drop, so which is a minus Rm into I2, Rm into, I'm sorry, this is not I2, this is I1, Rm I1, and this is equal to 0 as we are applying the KVL here. Okay, so let us write the other way. So E1 will be equal to now what? R1 I1 plus Rn I2 plus R2 I1 minus R2 I2 plus Rm I1, and then this I can write as E1 will be equal to R1 plus R2 plus Rm, R1 plus R2 plus Rm I1 minus what will be this, minus R2 I2. So this will be, what I will do, this will be R2 minus Rn I2. That way also I can write. Okay, let me check it here. Yeah, so that way also we can write, or again just like this way, R1 plus R2 plus Rm I1 plus Rn minus R2 into I2. Okay, this for mesh 1, and now I can write for mesh 2 also. So the same KVL I will apply here. Let me start from R3. So it is minus R3 into I2, it is again drop, so minus E2. I am coming here, so there is a rise, so this will be plus Rm I1, and again I am going this way, so this will be plus minus, so that's a drop, so it will be minus R2 I2 minus I1, that is equal to 0. And if you solve, so this you can write as minus E2 will be equal to minus Rm minus R2 I1 plus R2 plus R3 into I2. Okay, so this is equation 2, and with that we can make it into the our obtained the linear algebra form, so which will be unknown currents are I1, I2, and you can see in mesh 1 current going from positive terminal, and what are the batteries are connected, independent batteries are connected E1, so this will be plus E1. And if I am coming here, so current is coming into positive terminal, so it will be minus E2. And what will be this diagonal entry, it will be R1 plus R2 plus Rm, and this will be R2 plus R3, and this is minus Rm minus R2, and this is Rn minus R2. Okay, correct? No, I'm sorry, first let us solve this equation. R1 plus R2 plus Rm I1, Rn minus R2, so this is Rn minus R2. Now let us write this, so minus R2, I2 is R2 plus R3, and this will be minus Rm minus R2. Okay, so you can see that this matrix is not at all symmetric matrix. So with this we can conclude that if the network consists of the independent voltage sources, then you will get it the symmetric impedance matrix, and if the network consists of dependent sources, then you will not get the symmetric matrix, you will get it the asymmetric matrix. Okay. One more example, let us quickly write with some numerical values. So suppose let me take this, so there will be one voltage source, resistance, one battery source like this, suppose this is 10 volt, this is 3 ohm, this is for example 7 ohm, this is 4 ohm, this is 1 ohm with battery 4 volt, this is 18 ohm, this is plus minus let's say 7 volt, and this is 12 ohm, and again one more battery element, so this is suppose 12 ohm. Okay, so this is planar, then you can assign this is current, mesh current 1, this is mesh current 2, mesh current 3, mesh current 4, and from that you can directly write the equation. So for mesh 1 it will be the sum of all the resistances in mesh, so 7 plus 3 is 10, so this will be 10 I1 minus common resistance which is 7 into I2, and sum of all the sources, so coming out is plus, and that is 10, and going it into again coming out, so it is 10 plus 12, so this is 10 I1 minus 7 I2 which is equal to 22. Similarly you can write for mesh 2, so sum of which is 7 plus 4 plus 18, this is I2, there is common is minus 7, so minus 7 I1 plus 7 plus 4 11 plus 18, so this is 29 I2. Is there in common between 2 to 3? Yeah, it is common, so it is minus 18 I3. Is there any common between 2 to 4? Yeah, it is common, minus 4, so minus 4 I4, which will be equal to sum of all these voltage sources present, so current is going into the positive terminal. Again, is there any source? No. So this will be minus 12 volt. This equation 2. Similarly, you can write for mesh 3 also. So it will be 18 plus 12. So this will be something 30. So this is 30I3. Okay, is there any common between mesh 3 with 1? No. So this is 0I1. Is there any common between mesh 3 to 2? Yeah, 18. So it is minus 18I2 plus 13I2. Is there any common between mesh 3 with 4? No. So there is 0I4, and which is equal to voltage source is present in it. So observe that current going into positive terminal. So it will be minus 7 volt. So this is equation 3. Similarly, you can write for mesh 4. So 4 plus 1 5. So 5 I4. Is there any common between 4 with 3? No. So plus 0I3. Is there any common between 2 to 4? Yeah, 4 to 2 minus 4. So minus 4I2, and there is no common between 1 with 4. So there is 0I1, and which will be equal to, observe that current is coming into positive terminal. So it will be minus 4 volt. Okay, and then you can solve using the linear algebra form, and you can obtain the unknown mesh currents. Okay, so this is all related with the mesh analysis, to write the equations using mesh analysis if the network consists of independent voltage sources and the resistor network. Now next we will see what if the network consists of current sources. Okay, so there are two ways. One, we will see what if the current source is present at the outer mesh, and what if the current source is present in the common terminal of the mesh. So for that, let me take it to one example, and directly we will write. So this is 4, this is suppose 6, and let us say this is 1, and now observe that there is one current source present in it. So it is 2 ampere. Suppose this is plus minus 10 volt, 4 ohm, 6 ohm, plus minus 5 volt. Now say the problem is, again you find out the all mesh current, and actually find out the and do the power audit also. Okay, to confirm our interpretation. Okay. So let us find out what will be our interpretation from it. So suppose this is my mesh current 1, this is my mesh current 2. So now it has been asked to calculate the currents in all the branches. Observe that there are 2 meshes. Now here you observe that current source is present, so don't directly go to convert the current source into voltage source. Now here your problem has become very simple. Now you see that in the outer, the current source is present in outer mesh. So ultimately you know the mesh current too. You don't have to find out the mesh current in the second mesh, that is I2. Okay, because already second mesh current you already know it, because the current source present at the outermost branch, okay, or outermost mesh current. So one mesh current you already know. So this I2 I can write as the 2 ampere. Okay, so your problem has been solved by half of the problem has been solved. So don't think about the conversion of current source into voltage source, etc. Now let me write the equation for mesh 1. So for that, what it will be, 4 plus 6, sum of the resistances. So 6I1, resistance common between this with this is 6. So it will be minus 6I2, which will be equal to sum of the batteries. So current coming from positive terminal, so it is plus 10 going into positive terminal. So this is minus. So this will be 10I1 minus 6I2, which will be equal to 5. And already I2 you know, which is 2 ampere. So it will be 10I1 minus 6 into I2 is 2, which is 5. So this is I1 will be equal to 5 plus 12, it is 17 by 10. So it is 1.7 ampere. Okay, so now this is your 7 ampere, 1.7. So this is your 1.7 ampere. Okay, and this is your 2 ampere. Okay, so here it is 2 ampere. So obviously what will happen, previously we had assumed that the current is this, but now current will go from this and 8. How much is the current remaining? This I1 minus I2. So this is already previously what we assumed, the current in this common mesh was I1 minus I2, and I1 is how much? 1.7, I2 was 2 ampere, so it is around minus 3 ampere current, which is negative. So it means that whatever the direction we had assumed, what direction we had assumed previously, that this direction we had assumed, which was I1 minus I2 as per our convention we have seen. So this direction is not correct, so the current direction should be reversed. So what is the resultant current direction from this? So resultant current direction from this is like this. So 0.3 ampere should come, so that it will satisfy the KCL at this particular node. Okay. Now to check whether it is right or wrong, so that can be done by the power audit. So suppose this is my A and suppose this is my B. Now in order to do the power audit, I should know the current and voltages for each branch. Here I know current and voltage, here also I know current and voltage, here also I know this current direction is something like this. So this will be the polarities, and suppose this is 2 ampere. So I almost know voltage and current for every element. Now for the current source, if I am coming, I know the current, but I don't know the voltage. So for that I would like to find out how much is the voltage drop across this current source. So let me call B, A and B. So suppose VAB I would like to find out. So we know to find out the potential, I should go from terminal B to A. Okay. So if I am going in any path, so if I am going from this to this, so what I observe that VAB will be like this plus this. So here I observe that there will be the voltage rise, because current is, see this, our resultant current direction is like this, and this will be positive, this will be negative. So if I am going, voltage has been raised here. Okay. So how much is your voltage develop across this 6 ohm resistor? So it will be 6 into 0.3, so which is 1.8 volt, and then I am coming from here to here, so that voltage is dropping, which is minus 5. Okay. So how much is VAB, which we have assumed in this direction like this? VAB means the potential difference between A with B, where the potential is higher at A with respect to B. So VAB will be what? 1.8 minus 5, so which is minus 3.2 volts. So this, observe that it is negative. Okay. Means what? I have to change my polarity. So instead of like this, this was our previous assumed one, so this is not correct. So what should be our polarities? Polarities will be like this, plus and minus, because of this negative voltage drop we got it. Okay. So now this way we have found out the drop. Now let me do the power audit. So for that, if I would like to calculate the power, so we know that some of the sources may absorb the power, some of the sources may deliver the power. Okay. So let us find out individually. So let us find out power, whether delivered or absorbed by battery. So current coming out from positive terminal, so it will deliver the power. So this is power delivered by 10 volt battery, will be 1.7 into 10, which will be 17 volt, sorry, watt. Okay. Then let us calculate for power, whether delivered or absorbed by 5 volt battery. So you can see current coming from the positive terminal, as the value we got it as minus 3, so we have assumed the direction like this. So coming out from positive, so it will deliver the power. So how much it is? It will be 0.3 is ampere and 5, so it is 1.5 watt. Okay. Then this is over for 4 ohm. So obviously this will absorb the power, because positive terminal is coming out here. So power absorbed by this will be, say, you can calculate using I square R also. So it is 1.7 square into 4, then power this thing by 6 ohm, so it will absorb, so it is 6 ohm into I square is 0.3 square. Again, is there any one more resistor? No. Again, this is over, this is, now let us come here. So our assumed polarities are plus and minus like this, but current is coming into the positive terminal as our prism, given that the direction of current source is like this and we obtain the polarities this way. So what is happening, that current is going into the positive terminal of the battery, so this will also absorb the power. Okay, so how much it will be? 2 into voltage drop is how much? 3.2, so which is coming out as 6.4 watt. Okay, so now power delivered is 10 plus 5, so it is 17, plus power delivered is 17 plus 1.5, it will be 18.5, and power absorbed will be 1.7 square into 4, so this is coming around 11.56, plus 6 into 0.3 square, it is coming 0.54, plus 6.4, so if you add it, it is also 18.5. So with this, power delivered will be equal to power absorbed, and thus there will be power added, and with this whatever the current and voltages we have calculated, all are correct. Okay, so here only one point I would like to mention here is that it's not necessary that all voltage or sources will deliver the power, but some of the sources may absorb the power, and this is depend on the direction of the current source and the direction and the polarities of the voltage drop. Polarities of the voltage which we have been considered here. So if these are my terminals, positive and negative, so current is coming into it, so it means that our assumption was that current coming into the positive terminal of the battery, then it will absorb, and it will going out from the positive terminal of the battery, then it will deliver the power. Okay, now next we will see that what if the current source will be present in the common branch of the mesh. So because there are two possibilities, either in outermost or in common branch in the mesh. So suppose this is my resistor, then battery, then there is 4 ohm, and say this is my current source, direction is like this, then 6 ohm, polarities are like this. Okay, and then let me write, this is 2 ohm, for example this is 4 ohm, this is plus minus 4 volt, then this is 6 ohm, this is plus minus 6 volt. Now let us identify the meshes. There are two meshes. This is your mesh 1 with current assigned current I1, this is mesh 2 with assigned current I2, and this value is 2 ampere. We observe that this is 2 ampere is not the mesh current, now it is the common, right? So you can directly write I1 minus I2 will be definitely 2 ampere, but this current source will not be now the, like what we have assumed previously, that it is not giving me the total mesh current, but it is the difference between this will be 2 ampere, that is correct. Okay, now let us apply the KVL here. So in order to apply the KVL, I don't know the voltage drop across current source, so let me assume the voltage drop across current source is plus minus x volt, and let us write the KVL here. So let me start from here. So it is 4, okay, then sum of all the resistances, so which will be 6 I1, common between mesh 1 with 2, no, so this is minus 0 I2, and which will be equal to 4. So this is not correct, because I should know this drop also, I have to take it into consideration. So this simply I cannot write it. So what should I write? Because this voltage drop I don't know. Okay, so what I should write it? Sum of all the resistances, that is 4 plus 2, 6 I1 minus 0 into I2, and on the other side all the voltages. So current coming from the positive terminal, so it is 6, and here if I am assuming this direction, so current going into the positive terminal, so it will be minus x. Okay, so this is not 4, this is not 6, it is 4. This is equation 1, sorry, this is equation 1, this is equation 2, and let us write now for mesh 2. So suppose this is the thing, so 6 is only the resistance in mesh 2, so what it will be, I will write 6 I2. Is there any common between mesh 2 to 1? No, so this is 0 I1, and on the right side sum of all the sources, So I'm going from here to here, so current is coming into positive terminal, so this is -6, and already the current source has been connected this way. So what is happening, current is coming out from the positive terminal, so it is +x. So this is equation 3. Now it is very easy to solve. You can write I1 here is equal to 2 plus I2. You can substitute here, so it will be 6 into 2 plus I2, which is equal to 4 minus x, and this will be 6 I2, which is equal to -6 plus x. And then you can solve. 12 plus 6 I2 will be equal to 4 minus x, and 6 I2 will be equal to -6 plus x. And now there are two variables, unknown variables, and two equations. So with this you will get it, voltage drop across current source, as well as you will be able to know what is the value of I2. Okay, and once you know the I2, you will be able to know what is the value of I1. Okay, so this way you can solve the network instead of again thinking to convert the current source into voltage source. That is not the correct, good way to solve it, otherwise it will be complicated. Now these are the three possibilities that we have taken into the consideration, that how to write the equations with a very short duration of time if I have the different situation. There are three different situations. What can directly write if the circuit consists of only independent voltage sources? What will happen if the circuit consists of dependent and independent voltage sources? What will happen if the circuit will only consist of current source and the combination of current and voltage source? So this is the way we can directly write the equations. Now just have a look why mesh analysis is so weak than that of nodal analysis. Okay. So before this we will explain with the one example. So suppose I have the network like this. Voltage source present like this. R1, R2, R3, suppose R4, this is for example R5, R6, R7, R8. So this is planar or non-planar. If you look at it, it is very complicated, right? So this can be make it planar also. Okay, so there are, let us try to make it this planar. So one way what I will do, I will compress it and I will bring this point here, so that there will not be crossing on the branches. What I would like to say, just bring this point here. Okay. So previously how was the circuit? This, okay, which was R1, R2, R3 and R4. Okay, there was voltage source present here. Now I'm bringing like this, so 7 with this, so this is my point I bought here. So this will be what? One will be 7, R7 connected here. Okay, and R8 is also connected that with R3, so this will be my R8. So R7 and R8, then between R1 what is connected, R5 with that, so this will be R5, and between R3 it is connected R6, so this will be my R6. This is my R6. Okay, so with that, okay, this is my mesh 1, 2, 3, 4, 5. But other way is also what? Other way also we can make it planar like this. Previously say R1, R2, R3, R4, say R1, R2, R3, R4, then this I can make it R5 as it is, okay, R6 like this, and then this what I will do, I will shift here and this I will shift it here, okay, like this. I will remove this branch, to avoid the planar kind of representation. So this will be my R7 which will be connected here, and this will be my R8 which will be connected here, and there will be voltage source present like this, okay. Now you see these are my meshes, so they 1 2 3 4 like this, okay, and 1 2 3 4 like this. These are my meshes, these are my different kind of representation, okay. So actually this is non-planar, but we have converted into planar form, and what we observe that the same problem, but we are representing it into two different ways, okay. So meshes will not be same here, okay. So meshes are totally different. So this is the problem, that the mesh analysis somewhat weak method than that of nodal analysis. Or with this one more skeleton, if I draw like this, suppose one circuit is this way, okay. So here also, if you know, it is very difficult to find the meshes, okay. So that's why generally the circuit should be planar to apply the mesh analysis, okay. Because of to obtain the mesh analysis, to obtain the meshes are difficult. And again, if I am doing, there are so many ways to convert non-planar into planar, but the meshes will not same. Same. So with that, what can be conclude that the mesh analysis is somewhat weaker method than that of your nodal analysis, okay. So with this we stop here. We'll continue in the next class. Thank you very much.